In the previous lecture, you have seen the discussion on the conservation of two important quantum numbers, and those were actually the lepton number and the baryon number. Now in this lecture we will discuss the concept of another very important quantum number, which is called isotopic spin or isospin quantum number. Actually, the isotopic spin or isospin quantum number, or you may call it variable, this is actually applied to the strongly interacting fundamental particles. That means you can apply it for hadrons and their compounds, because you know hadrons are the fundamental particles which get strongly interacted. Okay. In fact, this quantum number facilitates the consideration of the consequences of the charge independence of the strong nuclear force. You know that neutron and proton, these two particles are actually called nucleon. Why these two particles have a common name nucleon, you can see. In fact, these two particles, neutron and proton, are simply the different charge states of the same quantity, of the same particle, not quantity, or you can say that this is the different charge manifestation of the same entity. Why we say that neutron and proton are not entirely different? They are actually only the different charge manifestation of the same entity, and so we call it nucleon. What's the reason behind it? Actually, there are basically three reasons which actually imply that neutron and proton are simply the different charge manifestation of the same entity. And those reasons are, you know, that mass of a neutron and a proton are almost equal, although neutron is slightly massive than proton, but that very small difference of masses of neutron and proton we neglect in general calculation. So we simply say that mass of neutron or proton are almost equal. Okay? And apart from this similarity, you know that the intrinsic spin of these two particles are also same. Both are actually a spin half particle, you know. And the third one is a very important reason, that you know that the nuclear force which acts between these two particles, that is nucleons, neutron and proton, and that nuclear force is independent of charge. It means the nuclear force acting between two neutron and two proton and a neutron and a proton, all these three interactions have same strength if the separation between the two particles are same. It means charge does not matter. When you say that there is a strong interacting force between neutron and neutron, both the interacting particles are chargeless. And when you say that there is an interaction between, let us say, P and, not P and N, but P and P, both of these interacting particles have charge, and in case of the interaction between a neutron and a proton, neutron is chargeless and proton is charged. But as these three interactions have equal strength, so we simply say that the nuclear force is charge independent. So these three similarity, that is almost equal mass, same intrinsic spin, and charge independence of the nuclear force, actually imply that neutron and proton are not entirely different. They are actually same particle, and that same particle is commonly called nucleon, but they have actually the different charge state. Okay, so same particle found in different charge states are neutron and proton. And this is the reason that the particles are grouped like isotopic grouping of elements. You know, when we say that isotopic element, in that case, you know that they have actually the same uh, charge number, that is the same atomic number, same place in a periodic table, and same properties. So in the similar manner, taking analogy from the isotopic grouping of elements, these particles are also treated as isotopes. Okay, although this term is not used here, but you can compare it. Okay, in fact, in this condition, the electric charge is treated like a variable, and this electric charge actually determines the different state of the nucleon. Okay, so when a nucleon is in the chargeless state, it is called neutron, and when it is in a charged state, then it is called proton. So this is these neutron and protons are same particle in different charge states, you may say. So I have mentioned here that the charge is treated as a variable for different state of the nucleon, and this variable is known with the help of a new quantum number that is called isotopic or isobaric quantum number. Okay, but you know that as I have told you earlier that this neutron and proton are not isotopes. So instead of this isotopic or isobaric quantum number, we use the term isospin quantum number. This will be in fact more appropriate. Okay. In fact, this isospin quantum number has same mathematical properties as that like a spin of the particle. So in other words, you can say that isospin quantum number plays the similar role as a spin quantum number plays in case of particles. Okay, and this similarity between the spin and isospin vector suggested the scientists to assign the value. In fact, this isospin quantum number is denoted by the symbol capital T or I, and as a spin of nucleon is in fact 1 by 2, so just as an analogy, scientists suggested that this isospin quantum number for nucleon, that is neutron and proton, will be 1 by 2, and for pion it is equal to 1. Okay. As I have told you earlier that this isospin has mathematical properties similar to the spin, but the mathematical properties of isospin and spin are identical, but don't confuse by this similarity that there will be a particular relation between the isospin quantum number and the spin. In fact, there is no direct physical relationship between the isospin and the spin. They are not related to one another directly by any physical relation. Okay. In fact, this isospin quantum number is used to find the energy states or the energy levels or quantum states of isobars, that is the system with the same number of nucleons. If two system has same number of nucleons, how we can decide that what will be the quantum states or energy levels? That is determined in terms of the isospin quantum number. Now, in fact, this isospin vector has actually three components, but its third component, which is also called Z component, is very important for the discussion of the characteristics of elementary particles. In fact, this third component of isospin quantum number is denoted by the symbol T3, or you may also denote it by the symbol Tz. Okay, and the value of this T3 or Tz actually depends on the value of isospin quantum number T. For a given value of isospin quantum number T, actually there are 2T plus 1 values of T3, which runs from minus T to plus T at a step of 1. You may also write here at a step of 1. A step of 1. It means from minus T to plus T, the values of T3 will lie, and so the total number of values of T3 for a given value of T will be 2T plus 1. Actually, this 2T plus 1 represents the 2T plus 1 quantum states. This is just analogous to the idea of a spin. You know that when you say that the spin quantum number of a particle is S, then corresponding to this S we define ms, magnetic spin quantum number, and you simply say that for a given value of S, there are 2s plus 1 values of ms. You simply say, and that values are actually from minus S to plus S at a step of 1. So in the similar manner, we simply say that for a given value of T, that is isospin quantum number T, there will be 2T plus 1 values of T3, and those values will be from minus T to plus T at a step of 1. Actually, we will find the values of T3 when T is known in the just now, and you will see how the value of T3 can be decided when we know actually the value of T. In fact, there are several ways to find the value of T3. I have discussed here only one method, but in nuclear physics, we also represent this T3 in terms of a matrix, and in terms of that matrix, we can evaluate the value of T3. But here I am giving you a simple formula to find the value of T3. Actually, this T3 is related to the number of neutron and the number of proton Z in a particular isobar. And what is the relation? Actually, T3 is given as Z minus N over 2. Z minus N over 2. Remember this formula. So, using this formula, you can easily find the value of T3 for different particles. For example, let us consider we have to find the value of T3. If you want to find the value of T3 for a proton, then what will be the value of Z? Since our particle is proton, so number of proton, that is Z, will be equal to 1. But when you say there is a proton, it means there is no neutron in that particle. Proton has only one proton, no neutron. So for this system, Z will be equal to 1 and N will be equal to 0. Now let us put these values of Z and N in this formula which I have mentioned in this equation 1. So for a proton, T3 will be equal to what? This will be Z minus N. Since Z is 1, so this will be 1 minus 0 because N is 0 and divided by 2. So T3 is equal to 1 by 2, or you can say plus 1 by 2 for a proton. Okay? And you can also find the value of this T3 on the basis of this idea when I have told you that the value of T3 is from minus T to plus T at a step of 1. And you can see for any nucleon, that is either for a neutron or for a proton, T is equal to 1 by 2. So taking T equal to 1 by 2, we can also find what will be the value of this T3 for a proton. You can see, since T is equal to 1 by 2 for a nucleon, and therefore T3 will be what? T3 will be 1 by 2 and 1 by 2 minus 1, and this is 1 by 2 and minus 1 by 2. So this is from T2 minus T. Okay. Now this T equal to 1 by 2, this state represents actually proton, and T3 equal to minus 1 by 2, this state actually represents neutron. Okay. So the value of this T3 for proton will be 1 by 2, and that of for neutron it will be minus 1 by 2. Okay. So you can find the value of T3 by this idea, by this concept too. And from this formula, it is very easier to find the value of T3 for a proton. You can see this is equal to plus half. Similarly, if you want to find the value of this third component for a neutron, you know, in case of a neutron, Z will be equal to 0 and N will be equal to 1. So T3 will be what? This will be 0 minus 1 divided by 2, that is minus 1 by 2. And just now I have told you that when you say that for a nucleon T is half, and so T3 will be plus half and minus half, this plus half is the value of T3 for proton and minus half for neutron. But is it strictly said that T3 will be equal to half for proton and minus half for neutron? No. You may use the convention that if we consider that T3 is equal to minus half for proton, okay, and plus half for neutron, that will be also correct. This is just a convention. Since nucleon has two different charge states, so this T3 which has actually two values, so first one represents a particular nucleon. If you consider that nucleon proton, then you say that T3 equal to 1 by 2 is for proton and minus 1 by 2 is for neutron. But if anybody please to say that T3 equal to minus half for proton, okay, and plus half for neutron, is it wrong? Answer will be no. This is just a convention. So we may use the convention that T3 equal to minus half for a proton and plus half for a neutron. You may use. Okay. In fact, in that condition, this formula will be changed. You can write T3 equal to N minus Z over 2. Okay, N minus Z over 2. So this equation 1, in this equation 1, this minus sign may be before Z or may be before N. Okay, both of these conventions are used. But normally the people use this first convention, which in which case you consider that T3 is equal to plus half for proton and minus half for neutron. This is just a convention. Okay. Now consider a system which is called dineutron. Have you heard about dineutron? When I have discussed actually the deuteron problem, then I have definitely told you about this system dineutron. In fact, dineutron means a system which contains only two neutrons, no protons. In fact, this dineutron is not a stable system. It is not stable, okay? But it is possible to construct a system which contains only two neutrons, okay? But remember, this is not stable, okay? Now, Since a dineutron contains two neutrons, no proton, so Z will be 0 for this. But number of neutrons in this case is equal to 2. So what will be the value of T3? You can see Z minus n over 2. Z is 0, n is 2. So 0 minus 2 divided by 2. And that will be equal to minus 1. So for a dineutron, which is an unstable system, for this T3 is equal to minus 1. Similarly, we also talk about another unstable system which is called diproton. No such nucleus actually exists in reality, so these are not stable. So when you talk about diproton, in this system actually there are two protons but no neutron. Okay, so T3 will be what? Z minus n over 2. Z is 2, n is 0, and so this will be 2 minus 0 divided by 2, that is plus 1. Okay. Now, you know very well, you have studied the deuteron problem, that deuteron is an NP system. In fact, this nucleus deuteron contains a neutron and a proton. So in this case, number of proton is 1 and number of neutron is also 1. So T3 for this deuteron is equal to 1 minus 1 over 2, and that will be equal to 0. So remembering that formula, you can find the value of T3 for such particles or such systems. Okay. Now, as I have told you earlier, that actually this quantum number, that is the isospin quantum number or its third component, actually determines the charge state of a particle, okay, particularly of hadrons. And in this regard, how we can actually determine the charge of a particle or a hadron or another part, not hadron but also another particle. For this, you can use a very famous formula which was actually given by the Japanese scientist Gell-Mann Okubo. Okay, and this is actually called Gell-Mann Okubo relation. And what is this relation? According to this Gell-Mann Okubo relation, charge of a particle will be equal to T3 plus B by 2. Okay, Q equal to T3 plus B by 2. Remember this formula. This is very important to get the value of charge of a particle from the concept of this third component of isospin quantum number. You should use this formula. Okay. Here actually this B, you know, is called baryon number. This is another important quantum number, you know. And you have studied in the previous lecture in very detail this baryon number. Okay. Now, taking this formula in our mind, we can calculate the value of charge of some of the important particles. For example, you can find the charge of a proton from this formula. You know, just you have seen that for a proton, T3 is equal to 1 by 2. Although I have told you that T3 may be taken as minus 1 by 2. This is just a convention. So we can take T3 equal to 1 by 2 and also minus 1 by 2. But this convention that T3 equal to 1 by 2 for proton is broadly used. So I have mentioned here that this T3 is equal to 1 by 2 for a proton. And as you know, for any baryon, the baryon number B is equal to plus 1. And you know that proton is a baryon. And since proton is a baryon, so definitely for it this baryon number will be plus 1. You have seen in the previous lecture that for a baryon number is plus 1. For anti-baryon, it is minus 1. And for other particles, it is 0. You have seen. Okay. So now you know the value of T3 and value of B for a proton. So using this formula defined in equation 2, you can easily find what will be the charge of a proton. So if the charge of a proton is denoted by the symbol Qp, then what will be this? T3. You can see T3 is 1 by 2. So I have written here 1 by 2 plus B by 2. Since B is plus 1 for a proton, so this will be plus 1 divided by 2, and 1 by 2 plus 1 by 2, that will be plus 1. So charge of a proton will be plus 1. Okay. But if you will consider that T3 is equal to minus half for a proton, in that condition, the charge of a proton will be equal to 0. It is not wrong. Although conventionally we always consider that charge of a proton has a positive charge, neutron has no charge. But this is just a convention. If you will take that charge of proton is 0, then you will see that charge of a neutron will be plus 1. Okay? It is just a convention that we consider that the charged state of the nucleon is proton and the uncharged state is neutron. This is just a convention. Okay. Now we will find the charge of a neutron on the basis of this convention. Again, you know, for a neutron you have just seen that T3 is equal to minus half, and since neutron is also a baryon, and for this baryon number will be plus 1. So what will be the charge of a neutron? This will be minus half plus half, that will be 0. But see, if you consider according to our convention that T3 is equal to plus half for neutron, in that condition charge of neutron will come out to be plus 1. Okay, this is not wrong, but this is unconventional. Simply people does not use such type of convention. Okay. Now we will find the charge of pions. You know, actually pions are found in 3 charge states, and these are pi plus, pi 0 and pi minus. How we can say that pion will be in 3 charge states? You have just seen earlier that the value of the isospin quantum number for a pion is equal to 1. You can see here T is equal to 1 for a pion, you can see. Okay. Now you have just learnt that for a given value of T there are 2T plus 1 values of T3, and all those values of T3 represent actually the different charge states or different quantum states of the particle. So since T is equal to 1 for pions, so what are the values of T3? This will be 1, another will be 1 minus 1, which is actually 0, and then this will be 0 minus 1, that is minus 1. This is the value of T, and this is the value of minus T. As value runs from T to minus T, so you can say that T3 will be 1, 0 and minus 1. Actually these 3 values of T3 represent the 3 charge states of the pion. Okay. Now again conventionally it is supposed that the value of T3 equal to 1 is for pi plus state, T3 equal to 0 is for pi 0 state, and T3 equal to minus 1 is for pi minus state. Okay. So there are 3 charge states of the pions: pi plus, pi 0 and pi minus. Okay. Now T3 is already known for the 3 charge states of pion. B is also known for this. You know, pions are not baryons. Pions are not baryons. And you know, if a particle is not a baryon, then baryon number for all those particles which are not baryon is equal to 0. So since pions are not baryons, so B will be equal to 0 for pi plus, pi 0 and pi minus. Or for all these three pions, B will be equal to 0. Okay, B will be equal to 0. Now use that formula for which is for finding the charge of a particle. You can see Q is equal to T3 plus B by 2. Okay. Now T3 is known for all the three states of pions. B is 0 for all the three states of pions. Okay. So now one by one we can calculate the value of charge of these three states of pions. First of all, the charge of pi plus, Q pi plus. For this, you can see it, I have taken this T3 equal to 1, so I have written here 1 plus B by 2, but B is equal to 0 for all pions, so this will be 1 plus 0, that is plus 1. And if you want to find the charge of pi 0 pion, Q pi 0, what will be that? For this you can see that the value of T3 is actually equal to 0. You can see here. And so charge of Q pi 0 will be 0 plus 0 and that will be 0. And charge of pi minus, if you write it Q pi minus, then this will be T3 plus B by 2. But T3 for pi minus, you can see here, this is equal to minus 1. Okay, you can see it here. So this will be minus 1 plus 0, that is minus 1. So in this way, using that Gell-Mann Okubo formula, we can find the charge of these particles. Okay. Now you know that due to the symmetry consideration, this isospin quantum number which are actually associated with hadrons, not with leptons, will remain conserved. But in which interaction this will remain conserved? You know, since isospin quantum number are associated with hadrons, and hadrons suffer actually the strong interaction. So you can easily say that this isospin quantum number will remain conserved only in a strong interaction. Okay, because this quantum number is associated with hadrons, and hadrons are the subject matter of the strong interaction. So isospin quantum number in any nuclear process will remain conserved only when that nuclear process is actually suffer the strong interaction. But the third component of this isospin quantum number, that is T3, remains conserved not only in a strong interaction, it also remains conserved in electromagnetic interaction. Okay, so you can say that T3 remains conserved in two interactions. First one is a strong interaction, another is electromagnetic interaction, but it will not remain conserved in weak interaction. Remember this fact. In objective question, such type of questions are asked that when there will be choices like or question will be the isospin quantum number remains conserved in which interaction. Choices will be a strong interaction, weak interaction, electromagnetic interaction, all of these. Answer will be a strong interaction. But if the question is T3 remains conserved in which interaction, answer will be both in a strong and electromagnetic interaction. Okay. So I hope you have understand the idea of this isospin quantum number. In the next lecture, we will see the concept of another very important quantum number, which is actually called strangeness. For strange particles, this quantum number is defined, and we will discuss it in very detail in the next lecture on this subject.